Geiger-Müller tube, GM tube. It's a detector which is used to detect the count rate of the radioactive source. Okay, so how much radioactive source is present in a certain location? We measure it in terms of the count rate. Okay, not in terms of like kilograms or cubic centimeters, not in terms of volume. We measure it in terms of the count rate. This tube detects the radiation, radioactive radiations. So each time it absorbs the radiation, it transmits an electric pulse to the counting machine. It makes a clicking sound or displays the count rate. The greater the frequency of the clicks, or the higher the count rate, the more radiation the Geiger-Müller tube is absorbing. Okay, I'm going to call it GM tube afterwards. So the procedure is very simple. Very simple. So you have the radioactive source. Let's say this is your radioactive source. You place it over here. And in order to detect what is the count rate of the radioactive source, you place the GM tube in front of it, and it is connected to an oscilloscope which would display the frequency or the count rate. Directly the count rate, you'll get the number as a count rate, let's say 30,000. So we'll get to know that the count rate is 30,000. So you just place the GM tube in front of it. It would detect the presence of the radioactive rays or the particles, and there might be number of clicks, and we'll have to count the number of clicks manually multiplied by the frequency or the range, or in our syllabus we just need to know how would the automatic one, the digital one, would do that. So it's just very simple, like measuring the speed of a moving vehicle with the IR sensor. So as the vehicle passes by, you have the transmitter, the receiver, you place it along with the vehicle, it would catch up the speed, it would be displayed on number. So pretty much the same as that one. So some of the specifications for this one are, first of all, the radioactive source must be placed very close to the detector. What's the reason for it? The reason is because we know that the alpha particles, they have the lowest range. They cannot travel that far. So what if we place the GM2 quite far, for example, at a distance of 40 or 50 centimeters? Okay, probably the beta particle or at least the gamma rays would be detected. But what about the alpha particles? Even if they are there, but still you'll not be able to get it on the GM tube, because they would not the GM tube is not in the range. So we need to place the GM tube as close as possible so we can measure the alpha particles as well. So we are at this one, describe the detection of alpha particles using cloud chamber or spark counter, and detection of beta particles and gamma radiation by using GM tube and counter. So for this one we can write they are preferably used to detect beta particles and gamma rays and alpha particle in our syllabus. Okay, otherwise they can be used to detect any of it, but for this one. Alright, then you have bit of the working. The working itself is not part of the syllabus. You should know how to deal with the numbers, what the procedure is, how do you display the readings, and that's it. And I'll show you some of the sample questions as well, and from there you can guess what kind of question they ask you in the exam. So this is a bit of the working. If you want to go through it, you can, or it would be better if you at least go through it. Otherwise you don't need to memorize it. All you got to do is to know what kind of instrument do you have for it, and how do you take the reading. That's it. So let's say here we have one of the question, a sample question from this GM tube detector. So the diagram shows the apparatus and used in an experiment in which barriers of various materials are placed in turn between different radioactive sources and detector. So you see, we studied one of the thing in the range. We studied this thing. Now alpha particles can be blocked by the sheet of paper. Then the beta particles are blocked by the by a thin sheet of aluminum, for instance, and the gamma rays are absorbed or blocked by the thick block of lead. So which table shows a count rate recorded by the detector of four sources? Which source emits alpha particles only? Alright, so let's start off with the option A. So this is a very interesting question. Let's start off with the option A. So option A says that when there was no barrier between the source and the detector, when there was no barrier between the source and detector, the count rate was 200. When you place a sheet of paper, the count rate is still 100. When you place the thin aluminum sheet, the count rate is still 100. And only once you place a thick lead, then the count rate was dropped to 30. So, does that give us any information that the radioactive source should be alpha particle only? The answer is no, straight no. Why? Because the alpha particles, they are able to be blocked by a sheet of paper. So in the option, you should be getting a thing that as soon as you place the sheet of paper, the count rate should have been decreased. So after placing the sheet of paper, the count rate should have been decreased. The count rate should have been dropped. Let's check out the option C, for instance. In the option C, when there was no barrier, the count rate was 1200. After you place the sheet of paper, the count rate is decreased. Okay, so far so good. But once you place the thin aluminum sheet, the count rate is further decreased. That means it has beta particles as well. Because alpha particles, they were blocked by the sheet of paper. Okay, well and good. But there were some beta particles as well, which are blocked by the aluminum sheet as well. So we have to look for the option which emits only alpha particles. Let's check out the option D. In option D, when there was no barrier, the count rate was 1200. When you place a sheet of paper, the count rate is still 1200. If it were emitting the alpha particles, then as soon as you place a sheet of paper, the count rate should have been decreased. So let's consider the option B. In the option B, once you place, first of all, without the barrier, the count rate was 200. So once you place a sheet of paper, the count rate has been decreased to 30. Count rate was decreased to 30. Once you place this thin aluminum sheet, the count rate is still the same. Once you place the thick lead sheet, the count rate is still the same. So the source that is emitting the alpha particles only is the option B. Then you might be wondering, okay, if the count rate was initially 200 and if we place the sheet of paper and we are blocking and we are saying that we had only alpha particle, then the count rate here should have been decreased to 0 and here also 0, and here also 0. But the thing is, we study this thing as a separate topic that we call background radiation. So this 30, the reading that you're getting, 30 count rate, this is the reading that you're getting as a background radiation. So this count rate would always be there as it is, even if there is no radioactive source. Even if you remove all the radioactive source, the background radiation would still give you the reading. So this 30 is from the background radiation. So for this one, B is the right answer. So let's take a look at the next one. An experimenter sets up the following apparatus in air to discover whether a radioactive source is emitting an alpha particle. The experimenter moves the paper between the source and the detector. There is no difference in the count rate. And you see the distance between the radioactive source and the GM tube is 30 centimeter. So you should be raising the eyebrows at this very thing that we studied, that the GM tube has to be kept close no more than 10 centimeters away. Especially when you know that there might be alpha particles which do not have much range. They cannot travel that much. So we gotta place the GM tube as close as possible. Now, why is there no difference? Even if we move the sheet of paper, paper does not absorb the alpha particles. That's wrong. They can. Let's check out the next one. The count rate due to background radiation is too high. No. Background radiation is generally not too high. The source emits beta particles and alpha particles, but this does not give any information about what's happening here. The radioactive source is too far from the detector. Yes, C is the right answer for this one. The radioactive source is too far from the detector. It should be at least or at a maximum of 10 centimeters, not more than that. Otherwise, you might be able to detect the beta particles and gamma rays, but you won't be able to detect the alpha particles.